Oh, you again. Back for more proofs? Well, unfortunately, we will not be working on proofs this time. But rest assured, we will have proofs again later in the semester, and they will be much harder than the ones last week. But this time we work on set builder notation, which I believe is considerably easier than proofs. Either way, grab a cup of joe, relax, take a seat, and try not to fall asleep watching this recitation video. So we begin with our first problem. It wants us to describe this set 0, 3, 6, 9, 12 using set builder notation. So what exactly is a set? Well, a set is kind of like a box, and this box can contain anything you really want it to. It can contain numbers, letters, socks, anything really. And but this one only contains numbers, and specifically they're integers. So we can try to describe our set a little more concisely. So we begin as such. Clearly, everything in our set is a multiple of 3, right? We have 0, 3, 6, and so on. So let's say that everything in our box is 3 times n, where n is some integer. But there is a condition here, right? So it's not just 3n, because 3n would imply it goes from negative infinity to positive infinity. It begins at 0 and ends at 9, including those two numbers. So we have the following condition. Of course, we define our n as well. 3n. n is in the set of integers, and it's on the condition that 0 is less than or equal to n, which is less than or equal to 4. This little pipeline, it kind of splits off the numbers or letters or whatever that are contained in our set with the condition applied to those numbers. So every number in our set is 3n, where n is an integer, and we apply the condition that n is less than or equal to 4, and it's greater than or equal to 0, right? Because 0 times 3 is 0, and 4 times 3 is 12. Okay, B. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. We do the same thing like we did up here. We have a bunch of integers, so we begin with n. Now n is specifically narrowed down to the set of integers. So n is in the set of all integers. Furthermore, comma, we have another condition. Negative 3 is less than or equal to n, which is less than or equal to positive 3. And we're done. We have C, MNOP. Okay, so let's say that we have some variable x. X is not a letter in this case, x is a variable. And it has the condition that x is in the set of the alphabet. And furthermore, we narrow down our condition even further. We say that m is less than or equal to our variable x, which is less than or equal to p. Okay, so determine whether the first set is a subset of the second is a subset of the first, or neither is a subset of the other. Our first problem reads the set of airline flights from New York to New Delhi, and then our second set is the set of nonstop airline flights from New York to New Delhi. So we have airline flights. In our first set, it's all airline flights between New York and New Delhi. In our second set, it's nonstop airline flights from New York to New Delhi. Now we don't have the information whether or not all of the airlines are nonstop, or if there are some that have stops, some that don't have stops. So our solution then would be, assuming that the second set is B and this first set is A, we would say that B is a subset of A. right? So it could be that all of the airlines between New York and Delphi are nonstop, in which case B would equal A. However, it's also possible that there are some airline flights from New York to New Delphi that have stops, in which case B would be smaller than A, which is why we're saying that B is a subset of A. So this subset symbol means that B could be the same size as A, it could have the same elements, it could be the same set, but it could also be smaller than A. There could be some airlines that are missing from B, but that A contains. Here we have the set of people who speak English, let's say this is A, and the set of people who speak Chinese, which is B. Is one a subset of the other? No. We would say neither is a subset of the other, because the set of people who speak English is totally different from the set of people who speak Chinese. Some people, in some cases, these sets might overlap, so some people could speak both languages, but that has nothing to say about A being a subset of B or B being a subset of A, right? You can know English and not Chinese, and you can also know Chinese and not know English. We have the set of flying squirrels and the set of living creatures. The first set is A and the second set is B. Well, clearly, flying squirrels are a type of living creatures, but there are many living creatures that are not flying squirrels. So we would say that A is a subset of B. Okay, for this one, we need to determine whether 2 is contained in any of these sets. A reads X is in the set of real values, so a real value is something like a whole number like 1 or 2, but it could also have a decimal like 1.5 or 1.52 or whatever. But we have the condition that X is an integer greater than 1. So although we defined X as being in the set of real numbers, we have a condition upon X that it has to be an integer. So I guess they could have also just put a little backward Z here, said that X was in the set of integers to begin with, but this is kind of a roundabout way of doing that. So X is an integer greater than 1. We know 2 is an integer and it's also greater than 1, so yes, 2 is contained in the set. For B, X is in the set of real values on the condition that X is a square of an integer. So we know 2 is not a square of any integer, right? So what integer squared is equal to 2? Right, nothing is. If this was not an integer, then this would be possible, but we have the condition that it's integer, so no. 2 is not contained in the set. Then we have a set given to us. It's limited, so it's not infinite like the previous two. It's 2, and the set that contains 2. Is 2 in this set? Well, it is. We have 2 right here. We would not consider this value a 2. This is a box or a set that contains 2, but that itself is not 2. So we can think of a set like this. Let's say this is our first set of parentheses here. And I'll color code it. And we have another set of parentheses right here. Well, we know that the element 2 is contained in our blue parentheses. It's contained in the outer box. And we have a set of inner parentheses, or curly brackets, whatever. But this itself is another set. Now, 2 is contained in those curly brackets. It is contained in that set, or in that box. But from the appearance of these outer curly brackets, from the appearance of this outer box, it doesn't really know or care what is in that inner set. It only sees a set and the value 2. So, therefore, yes, we would say 2 is contained in that set. Part D, we have the set which contains the set that contains 2 and the set that contains the set that contains 2. But we don't see 2 anywhere. So no, we have a box, but this box is just filled with other boxes. We don't know what's in those boxes. This outer a curly bracket or set can't see if there's a 2 in one of those boxes. So no. Part E, we have the set that contains 2 and the set that contains 2 and another set that contains 2 within that outer set. Kind of a mouthful, but we can see that no, we don't have a 2. And for the same reasoning, the set that contains the set that contains the set, which contains 2, also does not have the element 2 in it. Okay, so now we need to determine whether each of these statements are true or false. A, 0 is in the empty set. Now the empty set can also be shown like this. 2 curly brackets with nothing inside. But also it is often denoted as a 0 with a / through it. Anyway, is 0 in the empty set? Well, the empty set has no elements, so no. Is the empty set in the set that contains 0? No as well. Right? So remember, the empty set is itself a box. It's a box that contains nothing, but still a box nonetheless. Let's say that these 2 brackets around the 0 denote this box here. This set contains 0, but it doesn't contain any other boxes in it. So that's why we would not say that the empty set is in the set that contains 0. Now, if instead we had the empty set in the set that contains 0 or the empty set, then yes, the empty set would be an element, it would be in this set on the right. Now, what if instead of in, we said subset? Is the empty set a subset of the following? Is it a subset of the set that contains 0? Yes, because the empty set is a subset of every set, including itself. However, for part C, it reads, is the set that contains 0 a proper subset of the empty set? Now, a subset looks like this. It has a line underneath. Oops. A subset looks like this. It has a line underneath. A is a subset of B, for example. That means that A could be the same size as B, so they could have the same number of elements and the same elements as well. Or A could have fewer elements than B. However, with a proper subset, we don't have that line underneath. We don't have that equals condition as well. We're saying that A and B cannot be equal. B must have some elements that A does not have. In other words, A must be smaller than B in some way. So then, knowing that about the proper subset, is C true or false? You can say it out loud. It's false. I've been saying no, but my no's also imply false here. Okay, so the set that contains 0 is not a proper subset of the empty set because, right, nothing is a proper subset of the empty set, not even the empty set. Okay, so we have the empty set. Is it a proper subset of the set that contains 0? That is true. Yes, it is true. Because the empty set is a proper subset of anything that has at least some element in it. However, the empty set would not be a proper subset of itself because they would be equal, and a proper subset tells us that they cannot be equal. Okay, E, the set that contains 0, is this in the set that contains 0? Well, no. Over here on the right, we have a set that contains 0. We don't have, nowhere in here do we see a box that contains 0 as well. So if instead this said subset, then this would be true. But because it says in, it is false. F, is the set that contains 0 a proper subset of the set that contains 0? Now they are both equal, so no. It's false. G, is the set that contains the empty set a subset of the set that contains the empty set? This is true. They're equal, and remember, with a subset that has a line underneath, there's that added possibility that they could be the same. Okay, 2.2.2. A betokens the set of sophomores at your school, while B is the set of students in discrete math at your school. And we need to determine the following in terms of A and B. A says the set of sophomores taking discrete math in your school. So this is the set of students, which are in set A, but also in set B. In other words, where A and B overlap, kind of like a Venn diagram, which overlaps or intersects at the center. So we would say a student is in A and B. A and B. Recall the upwards facing caret from propositional logic. This is kind of an upwards facing U. So that's why it's very similar to the upwards facing caret. It kind of represents that they're both true in a sense. B says the set of sophomores at your school who are not taking discrete math. Well, this is the set of sophomores again, so we know A, but we have an intersection with a group of students who are not taking discrete math. This is the negation of B. So we have the intersection of the negation of B. Or in other words, it's also sometimes represented as follows. A intersection B complement, because that little dash above the B represents a negation in set theory. Okay, the set of sophomores at your school who are either sophomores or, should be an or are taking discrete math. So this is just like A, but instead of it being an and, this is an or. So this would just be A union B. It's a U for union, and it's kind of like the or operator from propositional logic. This is a set of people who are doing one or the other. So it's kind of like that downwards facing caret, but in this case, it's a downward facing U, which I guess would just be a normal U. The set of students at your school, either not sophomores or are not taking discrete math. So again, we have the word either, so we probably have a union, that same thing as an or operator in propositional logic. But we also have a negation of A and a negation of B. So we would get the negation of A or the negation of B. In other words, A complement union B complement. And this is the answer. Now we could also say that if we wanted to just complement the entire thing, we could complement this union, just how we can negate an or operator, and turn it into an and operator, turning this union into an intersection operator, or an intersection symbol in set theory. That would be, of course, A intersection B, and then we complement the entire statement. So either of these two would be a correct solution here. And this would probably be a correct solution. I think probably get away with that as well. We need to prove that A, or this expression on the left, is equal to the expression on the right. You may have seen this before. This is also called the distributive law from some table somewhere in your recommended reading. But anyway, there's two ways we can do this, or two ways we can begin. We can either begin with this expression here and show it's a subset of this expression here, or we can begin by saying this is an expression and it is a subset of this expression. We're going to have to prove it both ways either way. But let's begin by showing that A union B intersection C is a subset of A union B intersection A union C. Okay, so prove A union B intersection C is equal to A union B intersection A union C. And it wants us to assume that A, B, and C are sets. And so how do we go about doing a problem like this? Well, we want to show that the left expression is a subset of the right expression, and also that the right expression is a subset of the left expression. so we can begin either way. Let's begin with the left expression, right? So we begin like this. We say x, which is just some element in this larger set, is in the set of A union B intersection C. Then we use the definition of intersection and union to convert our unions into OR operators, like from propositional logic, and their intersections into AND operators. So then it would look like this. X is in A, or converting that union into an OR. X is in B, and X is in C. Right? And that's just the definition of union and intersection. From there, we can use the distributive law. Recall again from grade school, 2 times 3 plus 1, for example. We multiply the 2 against the 3, multiply the 2 against the 1, we get 2 times 3 plus 2 times 1. It's the same thing here. We OR x in A on x in B, and OR x in A on x in C. That would look like this. X in A union x in B, and x in A, or, I'm sorry, I just explained it that this union should be an OR. This and is brought down here, this OR is brought down here, and again we have the same OR operator over here, x in A or x in C. And now that's the distributive law as it relates to set theory. Finally, we can see that we basically already have our answer. This pretty much matches what we're looking for up here. So let's just convert those ands and ors into unions and intersections, and simultaneously get rid of that x in thing we've been using. So we have x or B intersection, our A union B intersection A union C. All right, and that would again be the definition of union and intersection. So we're halfway done. We've shown that A union B intersection C is a subset of the right expression, A union B intersection A union C. We have to still show that this expression is now is also a subset of this expression here. But notice this, that proof, that sequence of steps is just the same thing as what we've written, but backwards. So we begin here, we use the definition of union intersection to get this step. Then we use the distributive law backwards to get to this step. Again, we use the definition of union intersection to obtain the left-hand side of the expression. So this going down, we have that this expression is a subset of the other. Going up, we have that this expression on the right is a subset of the expression on the left. So because all of the steps are reversible, we would say that our expression A union B intersection C is equal to A union B intersection A union C. Now, we wouldn't be able to say this if some of these steps weren't reversible. So all the steps here are reversible, but usually when we have the step of addition, in which case we add a variable kind of out of thin air, kind of arbitrarily, this would not be a reversible step. Similarly, simplification, which drops a variable for the sake of what we're looking for, would not be a reversible step. So in that case, we would have to show both proofs, both ways, going from the left to the right to the left. In this case, however, the steps are reversible, so we don't have to do that. What can we say about the sets A and B? A A union B is equal to A. Well, this is actually only true when the following occurs. When B is a subset of A, right? So remember that the union tells us that this expression here contains the elements that are in A, but also the elements that are in B. If this union is equal to A, then that means that B, all the elements of B, must be entirely contained within the larger subset of A. In other words, B is a smaller subset of the larger subset A, and combining both of their elements just gives us A still. Part B, A intersection B is equal to A. Well, this is the opposite. We would say that A is a subset of B. A is a smaller subset, contains fewer elements, but has the same elements still as B, the larger subset B. Okay, for part C, A minus B is equal to A. So we take all of the elements of A and we subtract the elements of B. And we're left still with A. This can only be possible when A and B have no similar elements, no common elements. So in other words, A is a subset over here, and B is a subset over here, and in no place do they overlap. So A and B have no common elements. For part D, we have A intersection B equal to B intersection A. Now with this, this is simply the commutative property, right? We're taking the A and the B and we're switching their places. Nothing can actually be inferred by this knowledge. These sets are still the same. Nothing can be inferred about A or B in any other relation. So, nothing can be inferred. Finally, A minus B is equal to B minus A. And we'll see that this is only possible when A, the set A, is equal to the set B. We can also describe it as follows. A, which we could denote here, entirely overlaps with the set B. So A minus B leaves us with nothing. It leaves us with no elements at all. And B minus A leaves us with no elements at all either. That can only be true, again, when A is equal to B.